today from Rochester, who will be speaking to us about tiling bases and elementary combinatorics.
Hello, it's an honor and a pleasure to be here. And very happy to be at the University of Pennsylvania, see old friends, and also to give my first happy talk. So I've been promising Yumeng to give this talk for about a year now, I think. And I apologize for the delays, but finally this is happening. A few words about this talk. I'll talk about tiling basis in elementary combinatorics. The emphasis in this talk will be on self-containment and technique. I'll make almost no effort to discuss the historical background of this problem, etc., etc. And another point of emphasis will be an interaction of techniques from seemingly different areas of mathematics. Okay, so let's get started. Okay, so let's consider the unit cube in Euclidean space, okay? And let's consider the set of exponentials, e to the 2 pi I x dot n, where n ranges over the d-dimensional Euclidean lattice, okay? And it is quite well known that the set gives an orthogonal basis for L2 of omega. Indeed, this is what Fourier analysis is all about, okay? It is also quite interesting to note, I believe, that the unit cube tiles Rd by translation. Now, granted, this is just one example, but this does raise an interesting question of whether there is a fundamental connection between orthogonal basis and tiling. And this is really what this talk is about in a specific instance that I'm going to describe. Is there a fundamental link between orthogonal basis and tiling? Okay? So the study of this problem for a long time centered around the Fuglede conjecture. And so the Fuglede conjecture, which goes back to 1974, says that L2 of omega, so omega is a domain in Rd, has an orthogonal basis of exponentials if and only if omega tiles Rd by translation. Okay? In that same 1974 paper where Fuglede, whose name I'm horribly mispronouncing, it's a Danish name and I think it's something like Fuglede, but I make a fool out of myself every time I try to pronounce it correctly. In that same paper, he proved that this conjecture is true if either the set that generates the exponentials or the tiling set is a lattice. Okay, and based on this, the conjecture was formulated. If you assume that one of these is a lattice, then the dual lattice gives you the other. Okay, and the proof is a fairly direct argument using the Poisson summation formula. Now, in retrospect, so in mathematics, like everything else, everything is clear in retrospect. And perhaps one should have known back then that the case of a lattice is rather special, because within a decade of when this conjecture was formulated, various idempotent theorems were proved by Cohen and Mayer. And very roughly speaking, these theorems say that lattices are indeed very special. Namely, that if you have anything resembling the Poisson summation formula, then the set is very close to being a lattice. Okay? Nevertheless, before we talk about the extent to which the conjecture is true, let's mention some good news. And this is joint work with Katz and Tao in 2003 in dimension 2, Greenfeld and Lev in 2017 in dimension 3, and Lev and Matolchi in 2020 for d bigger than or equal to 4. So they proved that the Fuglede conjecture indeed holds for bounded convex sets. Okay? And just to mention in passing, the reason bounded convex sets are much easier than the general case is because it has been well known for a long time what the tiling sets for convex sets must look like. Okay? Or more precisely, it is known which convex sets tile by translation. they have to be polyhedra, and they have to be polyhedra of certain concrete types. Roughly speaking, they need to consist of rectangles and hexagons on their belts. Okay? And bad news is that what I quite often do when I give talks on this subject matter is I write the date of birth and death for the Fuglede conjecture. It was born in 1974, and it died a very miserable death at the hands of Terry Tao in 2003. In fact, I still remember getting a phone call from Michael Lacey telling me that Tao disproved the Fuglede conjecture, and I hung up on him. I thought that this was April Fool's, and then I called back in the afternoon and apologized. Okay? So Tao in 2003, and it was followed by work by Kalantzakis, Matolchi, and others, showed that the Fuglede conjecture is in general false in dimensions 3 and greater. And all of these results followed the same pattern. They produced a counterexample in vector spaces over Z mod P, where P is a prime. And then they used this beautiful idea by Terry Tao of transferring those sets into Euclidean space. Okay? And yes. So nevertheless, even though the conjecture was disproved, it did not kill the problem in the sense that the question still remains for which types of sets does the Fuglede conjecture holds. And even though it's not exactly true that orthogonal bases of exponentials exist if and only if omega tiles by translation, it still stands to reason that some kind of a connection exists, and there's much, much to be explored in this direction. Okay? All right. So as I said, all of the counterexamples were obtained in ZPD, where P is a prime and lifted to Euclidean space. So in a few minutes, I'm going to explain what exactly this conjecture means in ZPD, though you can probably imagine that exponentials are replaced by characters, and the concept of tiling remains the same. In fact, what Terry Tao did is he constructed a set of size 6 in Z in a 5-dimensional vector space over Z mod 3. He then constructed an orthogonal basis by hand. And then he noted that it's very difficult to take 3 to the power of 5 and divide it by 6, which means that the set cannot tile. Okay? And so until a few years ago, the only remaining cases were ZP2 and ZP3. And this is what this talk is largely about. In fact, I'm going to confine my attention to ZP2. Okay? The proof, even though, as you will see, is quite simple, it has what I believe are distinct and fairly simple analytic, number theoretic, and combinatorial components. And I think each of them is interesting in their own right. And I will do my best to emphasize where these components come into play. And here's the result. So this is joint work with Azita Mayeli and Jonathan Pakianathan. And that the Fuglede conjecture holds in ZP2 where P is prime. To be honest, this surprised us quite a bit, because once counterexamples started rolling, starting in dimension 5 and then 4, we really expected that perhaps this conjecture is just always false, except in dimension 1, where it's true for trivial reasons. Okay? Nevertheless, it turns out that it is true in ZP2, but it involves a number of miracles, which I'm going to now expose. Okay? So first of all, just a tiny bit of definition. So suppose you have a function from ZP2 to complex numbers. P is prime, and throughout this talk, I'm going to assume that P is congruent to 3 mod 4. When P is congruent to 1 mod 4, something extremely annoying happens, namely that square root of -1 is in the field. This does not fundamentally alter anything of what I'm going to show, but it adds a degree of technical complexity. Okay? So here we define a Fourier transform where instead of exponentials, well, we still use exponentials, e to the 2 pi I t over p. This also happens to be a non-principal additive character on Z mod p. Okay? And one can check by a direct calculation that the inverse Fourier transform formula works, okay, without the normalizing factor p to the minus 2. Okay? And one can similarly check that, that the Plancherel formula holds with a suitable normalizing factor. So there's a beautiful exposition of this in a book by Stein and Chakrachi, where they also point out that one can recover the corresponding formulas in Euclidean space by a suitable approximation argument, which is very, very pretty. And this is particularly interesting because in ZP2 or in ZPD in general, these are very, very simple formulas to check. All they require is geometric series. Okay? All right. Okay, so let's clarify the definitions. So let's say omega is in ZP2. What does it mean for omega to tile ZP2 by translation? Okay? And the answer is, it means exactly what you think it means. It means that if you take omega and you move it around by elements of subset capital T, then you cover all of ZP2 without overlaps. And how do you encode this? Using mathematical notation, it's just that if omega is an indicator function of omega, this is the usual abuse of notation, and capital T is the indicator function of the set capital T, then the summation of omega of x minus t, capital T of t, is identically equal to 1. Okay? This is just one way of encoding tiling in mathematical notation. Okay? And of course, this formula is reminiscent of a convolution. In fact, it is a convolution, okay? Which means that it lends itself easily to Fourier transform type manipulations. Okay? So if you sum the formula above over x in ZP2, it shows that if omega tiles ZP2 by capital T, then the size of omega times the size of capital T is equal to p squared, which is already clear from the intuitive notion of tiling. Okay? But this also points to something else that is special about vector spaces over Z mod P, and which sort of gives a hint as to why this problem is even tractable. And that's because primes, powers of primes have very few divisors. Which means that since omega times the size of omega times the size of t is equal to p squared, that leaves us with very few choices. Either omega is 1, that case is very easy. Omega is p, the size of omega is p squared, also very easy. Or the size of omega equals p. Okay, so just on general principles, we have reduced the problem to the case when the size of omega is equal to p. Okay, and this so we've now clarified the notion of tiling. So what about orthogonal basis? So we say that E of A is an exponential basis for L2 of omega. The space of square summable functions on omega means what? Means we consider a set of characters. Remember, chi of t is e to the 2 pi I over pt. So we take a set of characters where the frequencies live in some set capital A. And this capital A is a subset of ZP2. Again, chi is the additive non-principal character in ZP. In this case, it's just e to the 2 pi I over pt, as I said before. Now, it is slightly pretentious to be talking about L2 here, because every function from on ZP2 is square summable. Nevertheless, we need the structure to work with, and this is why this is mentioned. Okay. Another point is that if E of A is a basis for L2 of omega, then the size of A is equal to the size of omega, literally by elementary linear algebra. Okay? In fact, arguably, this whole problem is linear algebra because everything is completely finite. Okay? And so what are we trying to do here? We're trying to express a function from omega to, let's say, real numbers in the form f of x is a summation of the basis elements, chi of x dot a, times the coefficients. Okay? Where the summation is over the putative spectrum. Okay? So what does it mean that this family is orthogonal? So now what it means to express something, to express a function in terms of these exponential bases. So what does it mean that it's orthogonal? It means that, that if you sum any of these two exponentials against one another, you get 0. So summation of chi of x that a minus a prime is 0 for any a not equal to a prime. And in the language of Fourier analysis, orthogonality simply means that the Fourier transform of the indicator function of omega, evaluated at a minus a prime, is equal to 0 whenever a doesn't equal to a prime. Okay, so this is the orthogonality condition. Okay, and so it is also worth noting that if we sum both sides of this relation where f of x is expanded in terms of the basis elements, that these coefficients are simply equal to the Fourier transform of f evaluated at the elements of the spectrum capital A. In other words, everything here is very familiar from the Euclidean setting. Okay? So what have we done up to this point, just as a quick summation? We have stated a theorem that in ZP2, possessing an orthogonal basis of exponentials is equivalent to tiling. We have clarified the notion of tiling, right, where we wrote down the precise formula. And also from a simply visual point of view, it means moving the domain around and covering all of ZP2 without overlaps. And we've also clarified the notion of basis and orthogonality, where the basis property is the usual one. And orthogonality simply means that the Fourier transform of omega, the underlying domain, evaluated on the difference of two distinct basis elements is equal to 0. Okay? So now we're going to proceed to connect these two concepts. Okay. So since the very definition of orthogonality is forcing us to look at the zeros of the Fourier transform, this is where we're going to go. And now slightly improbable things are going to start happening. And so let's go for it. So suppose that the Fourier transform of omega is 0 for some m doesn't equal to 0. Well, let's think about what that means. So by definition, that means that 0 is equal to 1 over p squared, summation over x of chi of minus x dot m omega of x. But now we're going to play the following game. We're going to split it up into level sets of where x dot m equals t. So we're simply going to look at this x dot m over here. Okay? We're going to set it equal to t, and we're going to sum over t in ZP on the outside. We're going to give chi of minus 1 a name. We're going to call it zeta. Okay? It is also known as a primitive pth root of unity. And we obtain this interesting equation that 1 over p squared, summation over t, zeta of t, n of t, is equal to 0. Where what is n of t? N of t simply counts the number of points of omega on one of the p lines perpendicular to m. Okay? But there's something else going on here. Zeta is a p-th root of unity. And when we took algebra, we were told that this p-th root of unity has a minimal polynomial. And we just discovered another polynomial, seemingly of the same degree, that zeta satisfies. Okay? So let's go ahead and see what this means. Okay, so once again, the fact that the Fourier transform of omega vanishes anywhere not equal to 0 means that we obtain a polynomial in the p-th root of unity, okay, that the p-th root of unity satisfies, where the coefficients count the number of elements of omega on lines x dot m equals t, namely the lines perpendicular to m. Okay? So let's play a little game. Let's consider omega hat of Rm. So we're going to take the same vector where we got 0, and we're going to scale it. Okay? Then this scaling simply washes through the polynomial, and we get 0 again. Okay? In other words, what we have just seen is that if the Fourier transform of omega vanishes at a non-zero vector, it vanishes on any non-zero multiple of that vector. So miracles like this seldom happen in Euclidean space. Okay? And what else do we get to conclude? This is just the tip of the iceberg, right? So now what we need to do is bring elementary Galois theory to bear and draw some conclusions. So once again, we have that 0 is equal to n of 0 plus n of 1 zeta plus n of 2 zeta squared up to n of p minus 1 zeta to the p minus 1, where n of t is the number of points of omega on lines perpendicular to m. Okay? So what this says is that zeta satisfies the polynomial of degree p minus 1 with coefficients given by those n of t's. But we know that the minimal polynomial of zeta, as I alluded to a moment ago, is 1 plus zeta squared up to zeta to the p minus 1. And from this, we get to conclude that n of t is a constant. So amazingly, in ZP2, if the Fourier transform of a set omega is 0 on a non-zero vector, means, first of all, that the Fourier transform vanishes on the whole line, except for the origin, generated by the multiples of that vector. And secondly, omega is uniformly distributed along the lines perpendicular to that vector. Okay? So a very specific structure is emergent. Okay? And so suppose that we have an orthogonal basis for L2 of omega. By the discussion above, if you take omega hat at a minus a prime, the difference of any two basis vectors, you get 0. But if you multiply it by any non-zero scalar, you again get 0. And this is where the notion of directions enters the picture. Suppose that we knew that every possible direction is represented by the set omega. And what do I mean by directions? Exactly what you think it means, right? Is that you simply define an equivalence relation where the two vectors are the same if they're multiples of one another. And mudding out by this relation gives you directions. Okay? So if all the directions were represented, then we could conclude that omega hat vanishes on every non-zero vector. And that would mean that omega would be O of ZP2, which would render the problem very simple. Okay? And this brings up an interesting combinatorial question. And the question is there a simple way to conclude that a subset of ZP2 determines all possible directions? And the answer is yes. It's an emphatic yes. This various aspects, more difficult aspects of this question can be studied using Fourier analytic methods. One can ask whether the set of directions is distributed uniformly, etc., etc. But if we are simply trying to answer the question of whether every possible direction is represented, then we just need to think back to middle school. Okay? Well, it's what used to be middle school. What's going on these days is less clear. Okay. So here's just a very simple special case of a theorem due to myself, Hannah Morgan, and Jonathan Pagyanathan, is that if you have a subset of FQD of size bigger than q to the d minus 1, then A determines every possible direction. Okay? So what does this have to do with middle school? And that's because this is where we learned that if a direction is missing, then we can express this set as a graph of a function. This is not exactly what we were told, but it's equivalent. We were told about something called the vertical line test. But that's what the vertical line test means, right? So if there is a missing direction, you can indeed express all of your points as a graph of a function. Why is this significant? Because in FQD, if you have more than q to the d minus 1 points, you're never going to be able to express them as a graph of a function. Okay? And that is literally the proof. That means that if the size of A is bigger than q to the d minus 1, then A cannot possibly be a graph of a function, and that means that every direction is represented. Okay? So what does this do for us? What it does for us is that if you have an orthogonal basis for L2 of omega, and the size of A, the set that generates the orthogonal basis, is bigger than P, then omega must be all of ZP2. Since the size of omega is equal to the size of A by elementary linear algebra, as we noted before. Okay? So we have now reduced matters to, we have now eliminated the possibility that the size of A is bigger than P. But remember, a few moments ago, we had a discussion about what happens, what it means for omega hat to have zeros in the first place. If omega hat has a zero, means that it is uniformly distributed along lines perpendicular to that point where it has a zero. How many such lines are there? There are P such lines. And that means that if Fourier transform of omega has zeros at all, it means that the size of omega is a multiple of P. We have just eliminated all multiples of P that are bigger than 1. So we have now isolated the only meaningful case, namely where the size of omega is equal to P. Okay? Because the case is size of omega equals P squared, well, all of those have been eliminated, and the size of omega equals 1 is trivial. Okay? So it follows that if you have an orthogonal basis, then the size of omega is equal to P, and omega has exactly 1 point on P lines perpendicular to some non-zero vector M in A minus A. Exactly 1 point. Okay? So any picture one could draw here would be misleading because of periodicity. But try just visualizing P perpendicular lines and exactly 1 point on each of those lines. And it follows instantly that omega tiles by translation, because we can simply translate omega in the direction of those lines. And there's your tiling set. Okay? So the fact that omega has exactly 1 point on P lines perpendicular to some point where the Fourier transform is 0 immediately gives us tiling. Okay? And what this proves is that if L2 of omega has an orthogonal basis, then omega tiles ZP2 by translation. Okay? And one thing that I want to emphasize, because this is going to be used again, is that everything here goes back to what we call the magic lemma, which has two parts. The first part of the magic lemma says that if the Fourier transform vanishes at a non-zero vector, then it vanishes at every non-zero multiple of this vector. What this allowed us to do, in combination with the combinatorial idea of directions, is to eliminate all sizes of omega that were bigger than p. And the second part of the magic lemma is the one that allowed us to conclude, using very elementary Galois theory, that if the Fourier transform of omega vanishes on any non-zero vector, then it's uniformly distributed on the p lines that are perpendicular to that direction. Okay? Which, combined with the first idea, allowed us to reduce the problem to the case when the size of omega is p and has exactly one point on each of the p lines perpendicular to some vector which is in the difference set of capital A. Remember, capital A is the set that generates the putative orthogonal basis. Okay. So going back to where we were, we have shown that if L2 of omega has an orthogonal basis of exponentials, then it tiles. We still need to go in the other direction, and magic lemma is going to make another appearance. Okay? So suppose that omega tiles ZP2 by translation. So that means that there exists a set capital T in ZP2 such that summation of omega of x minus t times capital T of t is identically equal to 1. And one thing that I alluded to in the very beginning when I defined translation is that this is a convolution. And convolution behaves beautifully under the action of the Fourier transform. And in particular, so we have already noticed that we can reduce to the case size of omega equals p using the formula size of omega times the size of t equals p squared, right? But also, by taking the Fourier transform of both sides, we see that the Fourier transform of omega at m times the Fourier transform of capital T of m, remember capital T is the tiling set, is equal to 0 as long as m doesn't equal to 0. So let's just think ahead. Why is this good? This is good because there are two possibilities. Either omega hat is 0 somewhere. If omega hat is 0 somewhere, then the magic lemma kicks in, and we know that magic lemma is good. We like the magic lemma. Or omega hat never equals 0, but that means that the Fourier transform of the tiling set is 0 everywhere. If the Fourier transform of the tiling set is 0 everywhere, that means that capital T is all of ZP2, and that would imply that omega just consists of one point. We have already ruled out that case. We've already reduced ourselves to the case when the size of omega is p, right? So, right? So, as I said, either there is a non-zero vector where the Fourier transform of omega vanishes, or t is equal to ZP2, which is impossible because we have already reduced matters to where the size of omega is p, and thus the size of capital T equals p. Which means that we get to conclude that there exists a non-zero m such that the Fourier transform of omega is 0. And that means that omega has exactly one point on each of the p lines perpendicular to m. So now we have to work a tiny bit harder. So before, we drew the conclusion that we could tile omega in this case by simply translating along the lines. But now we need to go in the opposite direction and show that this set must have a spectrum. Okay? And we do this by a direct calculation. Okay? So one thing, as we've already noticed, right, since our set has exactly one point on P perpendicular lines, we can express this set as a graph, right, simply by looking in that direction. So what does it mean if we write it in notation? What does it mean that it's a graph? It means that there exists an orthogonal basis, E1, E2 of ZP2, and a function f such that omega can be written in the form TE1 plus f of TE2, where T in ZP. Okay? By the way, you know how I mentioned in the beginning that for the purposes of this lecture, I'm going to confine myself to the case P congruent to 3 mod 4 to avoid just technical nuisance. Well, this is one of the places where technical nuisance kicks in, is because when square root of -1 is in Z mod P, you have vectors, non-zero vectors that are perpendicular to themselves. Okay? And this just means that you have to fill up half a page handling that case. It's not a big deal, but this is why I made that assumption. Okay? So again, we have omega is TE1 plus f of TE2, where T in ZP. But this tells us exactly how to define the putative spectrum. We simply take the spectrum to be the set TE1, where T is in ZP. Okay? So instead of, so our tiling, we went in along those lines. Here, we're going in the other direction, right? And why does this give us an orthogonal basis? Well, again, okay, this is not quite middle school mathematics. This is undergraduate linear algebra. It is enough to check that capital A is an orthogonal collection, since the size of A equals the size of omega is equal to P. So once we check that, that capital A is orthogonal, since it's of correct size, we have everything that we need. Okay, so let's do it. So if you take a difference of any two different elements of capital A, what do you get? You get something of the form non-zero R times E1. So you get, so we have chi of minus TE1 plus f of TE2 dot RE1. But E1 and E2 are orthogonal. So we're just left with 1 over P squared, summation of chi minus RT, but this is a full exponential sum over the whole field, so we simply get 0 by geometric series. Okay? And this establishes orthogonality. Okay? So we have now shown both that orthogonality implies tiling, and that tiling applies orthogonality. And we did it by combining 3 basic components. Analytic framework was used to set up the problem. The notion of directions, combined with the magic lemma, which was algebraic in nature, was used to eliminate all omegas of size bigger than P. And this ultimately gave us orthogonality implies tiling direction. Okay? And then the magic lemma kicked in again when we proved that tiling implies orthogonal basis, because the magic lemma allowed us to, so first tiling condition, after we took the Fourier transform, allowed us to conclude that the Fourier transform of omega must have zeros. That allowed us to reduce to the case that omega has size P and has exactly one point on one of P perpendicular lines, from where we constructed the orthogonal spectrum by hand. And this completes the proof. And I'm going to stop there.